Hello everyone. I feel honored to report to you all on our latest progress in the area of cross-modal causal relation alignment for video question grounding, named CRA-GQA. The video question grounding task requires the model not only to answer the question but also to provide the precise temporal interval that supports the answer. However, existing methods face three major challenges. 1. Data bias. For example, the combination of baby plus woman corresponds to a severely imbalanced answer distribution. 2. Visual shortcuts or spurious correlations. Models often rely on visual features that are irrelevant to the question. 3. Sparse localization annotations. The cost of large-scale temporal annotation is extremely high. To overcome these problems, we propose the CRA framework, which eliminates cross-modal spurious correlations through causal intervention and achieves precise localization under weak supervision. The most representative work at present is the following one, namely the naive Gaussian-based attention mask. It directly assumes that cross-modal attention follows a Gaussian distribution and uses this attention for constraint during the video feature understanding phase. Although this approach can suppress noise, cross-modal correlation does not necessarily follow a Gaussian distribution, and the estimation of intervals is more inclined to adopt a post-hoc approach. LLM-driven data augmentation is also a very meaningful attempt. Using large language models to generate additional QA pairs to strengthen weak supervision. However, the quality of the augmented data is entirely dependent on the LLM's capabilities, and different ways of asking a question may not correspond to the same temporal interval. This means that the model cannot truly learn stable alignment patterns. To address these challenges, we propose a unified causality-driven solution, cross-modal causal relation alignment, CRA. Under weakly supervised conditions, CRA eliminates cross-modal spurious correlations through Gaussian denoising, contrastive alignment, and explicit causal intervention, thereby enhancing the consistency of localization and question answering. CRA consists of three core modules: 1. Gaussian smoothing grounding, GSG. End-to-end learning of a parametric Gaussian filter for cross-modal attention, which dynamically smooths and denoise the attention weights, directly generates more precise and robust temporal localization intervals within the model. 2. Bidirectional cross-modal alignment, CMA. Bidirectional info-NCE contrastive learning. Within the same batch, video segments are paired with non-matching QA pairs as negative samples to reinforce the mutual validation between video to QA and QA to video. Under weak supervision, this effectively enhances the strength of semantic alignment. 3. Explicit causal intervention, ECI. Linguistic backdoor intervention constructs a structured causal graph based on the syntactic dependency graph of QA, subject-predicate-object, to block spurious correlation paths from keywords to answers. Visual front door intervention treats the segments localized by GSG as mediating variables, generates uniformly distributed samples through clustering, and reconstructs the causal chain to quantify and neutralize visual spurious correlations. In GSG, we first extract features of video frames and QA using bit/BERT, then fuse temporal information through a two-layer transformer, and finally apply a learnable Gaussian layer, GS layer, to weight and smooth the cross-modal attention. In CMA, for each training batch, QA pairs and localization segments from other videos in the same batch are randomly sampled as negative samples. Contrastive losses are computed for both video to QA and QA to video directions, imposing bidirectional constraints. In ECI, on the linguistic side, graph convolutional networks are used to perform backdoor adjustment on the structured dependency graph. On the visual side, the front door formula is applied to compare mediating segments with uniformly distributed samples, thereby masking spurious correlations. Regarding causal intervention, we have performed deconfounding separately on the text and visual sides. On the text side, we were concerned that the model might simply memorize the high-frequency collocations of baby and woman with certain answers in the training set. To address this, we first decomposed each QA pair into a small syntactic graph with a subject-verb-object structure, capturing the core relationship of who did what to whom. Then, we used a lightweight graph neural network to transform this graph into a set of Debiassi linguistic features, so that the model could no longer exploit associations that are merely linguistic co-occurrences without true causal significance. Ultimately, it could only reason out the answer based on the true semantics of the question. On the visual side, we first had the Gaussian smoothing localization module output a key segment, the part of the video that the model deemed most supportive of the answer, and treated it as a mediating variable. Meanwhile, we clustered the frame features of the entire video to obtain a set of uniformly sampled candidate segments, representing visually unbiased inputs. During training, the model had to make predictions on both these uniform samples and the key segment. By comparing the differences between the two sets of predictions, we could eliminate visual cues that were only present due to data distribution biases rather than true causality. In this way, the model was left with only the most genuine and reliable visual evidence. The most crucial point is that the causal effect in the task can be quantified using weakly supervised grounding accuracy. We conducted comparative and ablation experiments on two major video question grounding benchmarks, CRA-GQA and STAR. On the CRA-GQA test set, CRA, using temp clip and frozen by LM as backbones respectively, outperformed all existing methods, including timecraft and naive Gaussian plus in terms of ACC at GQA, ACC at VQA, and IOP at 0.5/IOU at 0.5. On the STAR validation set, CRA achieved the highest ACC at GQA with an improvement of over 2%, and IOP at 0.5 with an increase of over 3%. Attention visualization. In examples from CRA-GQA and STAR, CRA can precisely focus on key frames, such as scenes of woman interacting with baby or tidying up the cabinet, supporting more reliable causal reasoning. Temporal interval length and proportion distribution. The segments generated by CRA have a distribution that is closer to the ground truth annotations, avoiding the bias of naive Gaussian plus towards overly short intervals. In the ablation study, Table 1 presents the ablation study results of the CRA framework, analyzing the contributions of key modules, GSG, CMA, causal module, etc., to performance. Removing any of these modules leads to a significant drop in ACC at GQA and IOP at 0.5. Among them, the CMA module is the most critical for performance improvement, followed by the temporal denoising effect of the GSG module. Table 2 shows the ablation study results using an advanced LLM, Quen 2.5-1.5b, as the text model in the NXT-GQA dataset. The CRA framework outperforms the NG plus method in terms of ACC at GQA, ACC at QA, and TIOP at 0.5, verifying the effectiveness of CRA in LLM integration. Table 3 compares the performance of CRA and IGV with the same ResNet plus BT backend. CRA significantly outperforms IGV in ACC at GQA, ACC at QA, and TIOP at 0.5, indicating that CRA's causal intervention and cross-modal alignment strategies are more effective in enhancing temporal localization and question-answering accuracy. In summary, our CRA framework effectively eliminates cross-modal spurious correlations and significantly enhances the causal consistency and robustness of video question grounding through Gaussian smoothing, bidirectional alignment, and explicit causal intervention. In the future, we plan to combine it with larger-scale language models to further explore causal structures and adapt to more complex scenarios and question forms.